Thanks for listening.
Hello, my name is Elena Rote. I'm an undergraduate. I've been lucky enough to work with this team. I'm going to talk about my project, which was improving speech feature representation based on linear discriminant analysis. This is a continuation of some of the work that Letta did, basically trying to engineer better features to improve the discovered acoustic units. This is how it fits into the big picture. So Letta's gone over knowledge transfer, multilingual bottleneck features, and this is a different approach that we're going to take. So we have our features of speech. This is simply representing the information contained in speech frame-wise, and it contains frequency information. And we put that through the acoustic unit discovery, which you've heard a lot about, and we get out the labeling. And of course, we can compare that to the true phones to see how well our system is performing. Okay, so next question is, what else could we use to represent the phonetic information in speech in a way that helps us discover better acoustic units? How are we going to do this? Well, when you look at the features that we already have, and you look at how we feed them through the acoustic unit discovery, the acoustic units are treating each frame of speech as if it were independent. And we know this isn't true because speech has a lot of temporal information. And it would be nice if we could somehow capture that and use it to train new acoustic units which have some awareness of what came before and what will come afterwards. So our idea was to add context to the speech features. In these experiments, 5 frames of speech on each side, each concatenated into a vector of 429 dimensions. So this is a little large. We would like to reduce the dimensionality. When you think about doing that, the first thing that comes to mind is PCA, Principal Component Analysis, basically taking high-dimensional data and projecting it onto the dimensions of greatest variability. There's a similar thing you can do when you know something about your data, when you know groupings. If we know that these points of data are clusters into 2 different groups, suddenly we're not really interested in what the data looks like along this axis. We really rather know what it looks like along this axis. So we do have labels for our speech features, which are the acoustic units which have been learned in an unsupervised way. So we can use that to project our speech features onto dimensions of greatest variance between labeled classes of acoustic units. So say we have 5 frames of speech. Now we come out with 5 LDA speech features, again in dimension 39. Okay, and after we've used that information to label, we simply put it back through the acoustic unit discovery, retrain, get out new acoustic units. Okay, so the top row is simply acoustic unit discovery on MFCC features, normalized mutual information 35.1. This is with the language model. This is with the language model that Luca mentioned. And when you take the output of that, perform LDA, and continue training the model that we already have, the normalized mutual information increases, and actually the number of discovered units doesn't change. And you might be thinking, well, you trained it for 5 more iterations and it went up. Surprise, but when you look at it graphically, you can see that there is a little bump beyond what was going to happen if we simply let the model continue to train. And so this is for unigram training in the acoustic unit model. But when you add bigram retraining, performing LDA still gives us a little bump on top, a little bump in normalized mutual information. So the conclusion here is that this is a lot of acronyms. performing linear discriminant analysis on acoustic unit discovery labeled null-frequency septual coefficients plus context yields a 1% increase in normalized mutual information. Now, Jinyi will come and talk about a different method of feature engineering.